So good days, everyone. Welcome to my talk. Today I'm going to talk about the application of the 3D graphene. Uh, actually, there are various applications that we can utilize these 3D structures of two-dimensional graphene material. Actually, the title will be from nanosensors to environmental sensings and mitigation. So it means uh, that we can do a lot of things with 3D graphene. So such as biosensors and chemical sensors. Actually, because I'm working in the field of my biomedical engineering, so the sensors that I made actually is normally will be biomedical sensors, and as well we can also use 3D graphene as uh, to the environmental monitoring, such as detecting heavy metals in water, and of course we can also use 3D graphene as um, the filter for organic pollutants such as glyphosate or something like that. So in this talk, we will cover all of the application, including also it might be possible we are going to publish our work in uh, in in a few weeks or so in the application of energy storage, and also we also work, but uh, toward the terahertz communication using graphene material as well. So you can see that the application is quite very important, but actually uh, uh, it is very useful to use this material as you see a broad spectrum of the application, right? Okay, so what exactly is the graphene? So it was invented in 2004, and it's one atomic thick. And actually, when we solved the Schrodinger equation to find the band structure, and we found that it is the dispersion relation is actually the photon-like. So the band gap is close, and it appears that the electron in graphene travel like wave, like a light. So actually, the velocity will be just 300 below the velocity of light. So it means that uh, it is quite the electron travel in graphene is very fast. That's why we have a very fast response in electrochemistry, and also when we want to tune um, the Fermi energy level of the graphene. So you can just adjust apply the voltage, and then you get the modulation of the Fermi energy level in graphene. So actually, the dispersion relation we will call it relativistic, and also the dispersion relation shows that um, the mass there's no mass of electron in the graphene. So, but what actually we can utilize further for the graphene, because if you have the flat one, the surface of the graphene will be just too small. Then we can do three-dimensional structure of the graphene. In order to do so, we could use the nickel foam as the catalyst, and then we let the gas of acetylene flow inside, and then we heat it up to 700 Celsius, and then we cool it down quickly. Then you get the graphene that is grow on the surface of the nickel foam, as you see in the figure. So you can see that there will be a lot more surface area of the graphene using 3D structure of nickel foam. Then you get 3D structure of the graphene as well. And then we use the pore size of around 100 to 300 micron of the nickel foam, and of course the graphene, the 3D graphene will be the same. Then now before we discuss about the application, so one application of this 3D graphene will be the sensor, right? That I mentioned before. So we call this kind of sensor is we use the Raman spectroscopy to identify the molecules, right? But actually, if you combine the graphene, the 3D graphene with the noble metal nanoparticle like gold or silver, then you get very high amplification of electromagnetic fields. And then we published the paper that we get a very high enhanced factor of the amplitude of the Raman scattering. So what actually is the Raman scattering? Actually, it is something that when you excite, it is the nonlinear optical process when you excite, for example, the visible light, and then it will go down from actually from G0, but when it relax, it go down to G1 because of the vibrational energy level for different molecules. Then you get different frequency that is output from the excite frequency. So the shift of the frequency will be the signature of that molecule. So if we have large enough amplification gain or enhanced factor, so to say, then you can identify the molecule, the trace amount of chemical substance, for example, tumor biomarkers for many disease or even cancer, like that. So then actually I would like to skip this one. I would just talk a little bit like it could happen if we have the right polarizability condition. So if the first derivative of polarizability is not zero, then you get the two frequency that could be output, which is the excited one and plus minus the vibrational frequency of the molecule itself, which is the signature. So we call it Stokes or anti-Stokes. So actually, we skip this page and we go. And of course, if you excited the nanoparticles with the laser light or electromagnetic field, And if you could confine this energy to the small volume, then you could amplify the electric fields. So the effect that occur is the oscillation of the electron in the nanoparticle. We call it localized surface plasmon. Okay. So then if you shine the light, especially visible wavelength, and actually the dielectric of this material will be negative, and you will see later on that it will amplify these electromagnetic fields, and then therefore it enhance or increase the amplitude of the Raman spectroscopy. Okay, from this equation that you can when we using Maxwell equation to solve the nanoparticle as a sphere and putting all the dielectric, you see that there will be the denominator of the dielectric of the metal and the environment. But in the visible wavelength, we could use Drude model to model this one, and we found that actually it is negative, and then therefore the denominator could be make it to approaching zero, and then you get a very high electromagnetic field or electromagnetic field. Okay, and that's why we will combine this one to the 3D graphene, and finally we found that we try to use the methylene blue, and then we found that even picomolar concentration, we can still detect the peak of the methylene blue. So that's why it is very promising that we could achieve uh, like in order to detect the early stage cancer, you must be able to detect the trace amount of um, the biomarkers of that cancer. Okay, if you could detect trace amount of that biomarker, then you can detect the cancer at the very first stage, very early. Then you can cure the cancer before it happens, right? So this work, we just illustrate that when we combine the two uh, structure which we use, we sputter a nanoparticle onto the graphene foam, and then actually the graphene will acting as the mirror to the nanoparticle and enhance the plasmonic effect as well. And we have also the theory uh, to actually we check, okay, we get the graphene, we get the nanoparticle, and we check the extinction wavelength. So we use 700, and this is the result. When compared to just only normal silicon or some other material, actually the graphene foam hybrid with the nanoparticle is the best. Then I would like to skip because we don't have time, but I would just to say a little bit about this. The mechanism is that if you have a multi-layer of of graphene, right, then you get the amplification for many times. We call it cascade amplification, and that's why you get very high amplification of this structure, 3D structure of the graphene. So in conclusion, for the first application, you combine the 3D graphene with the silver nanoparticles, and then we get the enhanced factor uh, that could be able to detect even from nanomolar of methylene blue to picomolar or even to 100 micromolar, which is the range is quite uh, broad. So it is good for the sensor to do that. And the specificity is the best. So now we will come to the next one that we use it further in electrochemistry to detect the kidney injury. So actually, normally when you take the blood test, they will test you. They will check your blood and check if the how much for the creatinine in your blood sample will be, and they will calculate the filtering rate for your kidney. If it is too much creatinine, then that means your kidney is damaged. But instead of doing that, we have something else. We call it NGAL. So the NGAL is um, the protein that the neutrophil will come when the kidney is damaged. So, but the usefulness of NGAL is that the response is just 2 hours. So after your kidney is damaged from maybe you go to marathon and then you're running and then um because it will destroy your muscle, and then the kidney need to filter the proteins, and if it damaged, then you can die from running the marathon. Then people actually die from running too long. So if it is possible that we could detect it earlier, don't, then we do this research. We use the NGAL um, from the urine, so not from the blood. So we can use the 3D structure of the graphene, and with the nickel layer, without etching out the nickel layer, we create the dipole, right? And then the dipole will pull the NGAL toward the receptor, and then we use the ferrocyanide as a mediator uh, to cycle the electron. So then finally we get the result that is very good, that at the redox potential we get the curve for different concentration of NGAL. So if it is maybe above 30 nanogram per milliliter, or 30 to 50, if it is above that, then it means that your kidney is damaging. So you have to stop doing that activity, or the food that you eat is poison, right? So you can see from the graph here that you in the that we can trace back to the concentration of the NGAL to detect your kidney without taking your blood sample. So it is very good. Then so so the next application will be um, to sense the arsenic in the water. So actually, we use the same structure, but for arsenic, it is more simple because it's not biomaterial. Actually, we will have the right redox potential for arsenic. And also we modify the graphene foam with we try to we try to we try to dope it. We try to decorate it with the iron. And actually, when the graphene, which is purely carbon, combined with the iron, it will appear to be nanoflower. So what is good for the nanoflower? Actually, it is good because you have more surface. You have more surface site for the interaction to occur. So when the arsenic with the charge 3 plus come, then as you see in the picture that we have three unpaired electron in the system of the nanoflower, and it match with the arsenic, right? So when it bind together, it gives us the electron. Then you can sense the arsenic easily. For example, in water or in rice, which is very essential because uh, you can eat only rice and then die, because actually you in the rice there's a regulation that you have to check how much arsenic that contains in rice. And actually we need the sensor to do so. But before we do rice, then we did it in the water first. So we are successfully do it. Okay. So finally we could detect we have a beautiful graph again, and we could detect as low as 1 pp part per billion. So then you can check, you can use the sensor to check if the 3D graphene to check if the water is contaminated with actually if you change reduction potential, you can check even with other heavy metals. So good. So I think for mitigation, actually we try. So we put the very small piece, like in the dimension of 0.5 centimeter square, and the thickness of 1 millimeter of the graphene foam or the 3D graphene. Then we just put it into the 1 liter of water, and then we put all the glyphosate that with very high concentration, like 10 ppm or something. Actually, it's spread all everywhere, even in our supermarket, because they use a lot of this glyphosate to get rid of the weeds. So we can see from the graph that even actually in 15 minutes or 20 minutes, it pull down the concentration of the glyphosate from the water. So it is very promising that actually we are going to publish this work. And also actually it could also filtering out the heavy metal as well, but with other conditions. So it is very promising that it can not only that it can be a sensor, it can also use to treat the water as well. So the utilization of this material is very good. And last but not least, I would like to talk about the energy storage. So actually we discovered that at certain condition, we have a equal step of the current that step up when we charge in electrochemical system. Actually, we are going to publish this work as well. So it is confidential, and we found that because of the jump of the current, you can make a very fast charge, and then we calculate the energy density, and we found that it is outperform the lithium sulfide battery, and we get around 3.5 kilowatt hour per kg. So it is, I think it is better than lithium sulfide or something. So this work will again is publishing right now. It is confidential, so but we have a preprint. You can go to the link and then you can read that. Okay, so the last one, as terahertz communication, we could do the optical modulator to switch on and off light using the graphene. So you see the graph on the left-hand side. If you apply the signal to the electrode, then you change the Fermi energy level of the graphene, right? Then if the Fermi energy level is too low, then the light then the light that comes in would could not the energy is not enough to make a transition. But if the Fermi energy level is increased near to the K point, then it is possible for the interband to happen, right? So the light can go through the graphene. But if the Fermi energy level is too high, then it's not possible for the interband because of not enough energy of the electron to excite from the lower band to the upper band, right? So then from this principle, we could do the structure of the silicon photonic and make a modulator that let the light coming out or switch on and off. Because of the graphene electron in graphene is very fast, then you can do terahertz switching, right? So that's it for today because the time is too short. I'm so sorry. So but anyway, you will get the idea that actually, oh, it is the 3D structure of the graphene is very useful uh, in doing photonic sensor like to enhance the Raman spectroscopy. We call it surface enhanced Raman spectroscopy or SURF, or even with electrochemistry that we detect the trace amount of the NGAL in the urine, and then we could say that, oh, people are suffering from kidney damage. Okay, we call it acute kidney injury, actually. And actually, we could do also for the environmental sensing, like arsenic sensing, and we also it is possible also that we use the 3D graphene to absorb the organic pollutants such as glyphosate efficiently, and finally. We could do the energy storage in the I think in the near future. It is candidate, but and also for the terahertz communication, we could use it as optical modulator for very fast terahertz, but the power for switching is very low in the unit of femtojoule per bit. Thank you very much for my for invited talk today. So if you have any question, please feel free to ask. Thank you very much. มือสั่น